So hi everyone, I'm Olivier Blazy, so welcome to the first talk of the cryptographers track of RSA and the first session about public key cryptography. So I'm going to speak about public key identity-based revocation scheme, fully attribute hiding, and function private. So I'm a professor at Ecole Polytechnique, and this is a joint work with Sayantan Mukherjee, who is at IIT Jammu. Okay, so the main purpose of this talk is to speak about predicate encryption, and a predicate encryption is some special kind of public key encryption where decryption is possible if a predicate is verified. So it means this is some relation between a secret embedded in the ciphertext and some secret possessed by a user is verified. So it's a generalization of standard public key cryptography where you have a secret key associated with a decryption key associated with a public encryption key. Here it can be a little more advanced. And two of the main kind of predicate encryption that I studied are inner product encryption and identity-based multi-recipient encryption. On inner product encryption, we are going to consider the inner product between a secret Y that is hidden in the ciphertext and a secret possessed by the user X. And classical version, so zero inner product encryption, you're going to be able to decrypt if your secret is orthogonal to the secret embedded in the ciphertext. And variation is non-zero inner product encryption, and it's the opposite. You're able to decrypt if and only if your secret is not orthogonal to the secret hidden in the ciphertext. For identity-based multi-recipient encryption, it's a generalization of identity-based encryption. So normally, with identity-based encryption, you are encrypted for one user, and you are stating that, okay, only Alice is able to decrypt the ciphertext. Here, you have the broadcast version, where you're going to say every person who is a female cryptographer, for example, can decrypt the ciphertext. And so all the identity in this set are going to be able to decrypt. And you have the opposite. You can do identity-based revocations. So it's everybody who is not inside the set that is able to decrypt. And so we're going to try to link all those primitives together to show that, in fact, it can be done, it can be achieved in the standard model with full security. Okay. So when we speak about security for the scheme, we have four main kind of properties that we are going to expect. So the first basic one is confidentiality. It means that if an adversary picks two messages, M0 and M1, we give him an encryption of one of them. He should not be able to guess which message was encrypted as long as it is not authorized to decrypt the ciphertext. So that's really the direct equivalent of indistinguishability that you have on ciphertext. Then we want more advanced properties, so that are called either weak anonymity or weak attribute hiding. It means that if I give you a ciphertext, for a challenge Y0 or Y1, you should not be able to guess which of the two challenges I used. And for the weak version, as long as you are not allowed to decrypt for those challenges. In the full version, it's a little bit stronger. You should not be able to guess if I use Y0 or Y1 to mask, to generate my ciphertext, and that either if your keys are not authorized or if they are authorized for both ciphertext. So it means that even if you can decrypt, you should not know for which challenge you are able to decrypt. You should just know that your key is working. And then you have another variant, which is predicate or function privacy. And here it's when I give you a secret key, you should not know which set of constraints your secret key is associated with. And so if you come back to the previous slide, you should not know whether I encrypted it for X0 or X1. And here it's something that you may want or may not want depending on the application. Case where you won't want it is like when you receive a key, normally you like to know for which set of attributes you're able to decrypt or to do something with it. And so in this case, you don't really want function privacy. But if you are generating keys for a set of users, for example, attendees to a conference, you may want to hide some special access or some special information associated with the key. Okay, so already some generic transformation exists. So you have a transformation from inner product encryption to identity-based multi-receiver encryption. And those transformations, their main purpose is to preserve confidentiality. And if you go to the subcases, so the cells that were on the right, then you can convert anonymous or fully anonymous zero inner product encryption to anonymous or fully anonymous identity-based broadcast encryption. However, we don't know how to build until now, fully anonymous zero inner product encryption. So this transformation is nice to be generic, but in fact, it's never happening because something doesn't exist yet. And you have the same for function privacy on identity-based revocation. Okay? And so we have this problem, and the main trick is that the generic transformation on inner product encryption don't preserve function privacy, and we wanted to solve that. Okay. So to come up a little in more detail on the properties that we want, so the first one is message hiding. And so to define the security experiment for message hiding, we are going to have a set of algorithms. And so the setup is just here to generate public keys and secret keys. And so, of course, the adversary has access to the master public key and hopefully doesn't have access to the master secret key. Then the adversary is allowed to do key queries. So he's going to get identities from a set, and he's going to get the secret key associated with those identities. And the adversary is going to provide a challenge message, so M0, M1, and M1, and a set of identity. We want this set to be polynomial sized because otherwise there's an issue and you cannot just run the algorithm. And is going to provide all identity in the set. And we are going to return the encryption of one of the message for this set. So if we are in the case where we want revocation, it means that for every identity in the set, the adversary is not able to decrypt, and for every identity outside the set, he should be able to decrypt. The adversary is still able to do key queries for identities in the set. And the adversary is going to output it guess, and he's going to win if he manages to decrypt the message, even if he never got a key that should allow him to decrypt. Okay. If we go to attribute hiding, it's somewhat the same, except this time, instead of considering the identities, it's going to provide set of identities. It's going to provide messages and two different sets of identities. The set, again, needs to be polynomial size, otherwise there's a problem in the definition of the issue. And we're going to encrypt according to one of the sets, and it should not be able to guess which message was encrypted and for which set. And so, again, we have the switch from weak attribute hiding, where the identity should not be authorized, and full attribute hiding, either they are not authorized or both are authorized for both sets of identities. So it's just a matter of allowing the adversary to possess more information and still remain secure. Okay. And the last property is function privacy. And again, it's somewhat the same, except this time the adversary is going to have a secret X embedded in the key. And the way we represent the secret here, we need to consider distribution of the secret to get some way to consider the fact that they are hidden. And so the distribution should be somewhat similar and independent. And the rest of the experiment is going to run somewhat the same. And again, the adversary should not be able to guess which thing was encoded and for X, which X was hidden. OK. And so where we are is that there's a gap in the ecosystem. And so there's many zero inner product encryption, but there's no non-zero inner product encryption scheme in the standard model, even if weak anonymity. And here it comes from the fact that the classical way to build ZIP is to use some kind of linear encoding to achieve a linear secret sharing. And so what's going to happen is that we're going to have some terms that are going to be computed to generate some kind of keys. And this term is going to be an element in the target group raised to a value beta, which is going to be the main secret, plus some function of the inner product. And the adversary is going to be able to compute this value in some way, hoping on the fact that the inner product is 0, and so we will have some kind of magical simplification. And so if you take the two terms that are presented, you have gt to the beta plus gamma, gt raised to minus k times gamma plus some delta of the inner product. The adversary, if he possesses k, he can simplify on the last term the minus k gamma to a minus gamma. And if xy is equal to 0, then he can simplify on the first term, recover gt to the beta, and be happy and do a one-time pad to decrypt the message. And so that you can do it normally when you are able to converge to one single value and you need the fact that the inner product is 0. But in case where it's non-zero, then it's complicated because you are just saying it's a random value that is not null. And you cannot have this kind of reconciliation that was nice to build a zero inner product encryption. And so here it's a problem because either you are able to explicitly compute this value, which is somewhat opposite to the fact that you are going to hide x and y also. And so we needed to find a way to do it. Anyway. And so to do so, we process in several steps. And so first we construct n predicate only zero inner product encryption in the binary group and show that it's fully attribute-hiding and function private under a new assumption. So just because we introduce a new assumption, we also prove that it's secure in the general group model, but it's normally a reasonable assumption. And then we produce a compiler, so generic transformation from predicate only the IP into an IP, and shows that this compiler preserves all the properties that you have. And so this way we obtain an IP that is fully attribute-hiding and function private. And while we're doing this, we also show that this transformation, we can take the initial transformation from inner product encryption to identity-based multi-receiver encryption to do an IP to IBR, and so build also a first efficient, somewhat identity-based revocation system. And so, and again, we show that this preserves the properties. Okay? So our scheme is this way, which is somewhat ugly, but in fact, it's an adaptation of the Killspan V15 quasi-adaptive zero-knowledge proof framework. And so, in fact, the thing that is scary about it is that it's using matricial notation, and it tries to be very generic. Does that work? Yes. But in fact, you can, when you have an element that is in bold font without square around it, it's just a matrix of discrete logarithm. So at the beginning, we are generating several discrete logarithms. So think of that as secret keys. And in fact, it's exactly what we say. We say that the master secret key is going to be all those matrices of discrete logarithm. Then the public key, in a standard Telgamal scheme, for example, it's often a group element associated with the discrete logarithm. And that's what is said when you have brackets, square brackets. It means that you have the associated the group element associated with the discrete logarithm. And so it's just matrices of group elements. And when you have a product, so it's a group element raised to a scalar, so it's still a group element. Except that you don't know, the adversary will not know the discrete logarithm, so he will see that just a plain group element. And so we have lots of elements that are generated, but it's somewhat classical and elegant in the design. At least you have some structures that appears. To do the encryption, we are going exactly the same way. So we're going to pick some random elements that are going to be discrete logarithm, generate a ciphertext with a main element, like in your Gamal, which is H to the R, but it's noted SA because it's a matrix. The ciphertext is a little more involved, but it's somewhat the same. We are hiding the secret Y in it, and with an extra term to avoid some kind of probability. And the ciphertext is going to be this set of elements. The keygen is the same, but on the other side. So we are going to take the X secret, hide it a little the same way, go into the other group, so in group 2 instead of group 1, generate the element, and the key is going to depend whether we are on J0 or 1, but that's more or less the same. And to test, we're just going to do some kind of pairings. And if the pairing match, we say that we encoded the message 1. And if the pairing don't match, we say that we encoded the message 0. What's interesting with this kind of notation, in fact, we can rely on many, many different kind of hypotheses. If k equal 1 is just the standard Diffie-Hellman or symmetric external Diffie-Hellman version, so it's your Gamal and the matrices really collapse to 2 elements. If k equal 2, then it's a decisional linear problem, if you prefer symmetric curves. And it's the same way, and here the matrices are going to be 2 times 3 elements, so 6 elements. 2 times 5, 3 times 5 elements. But it's the same, and you can take k as big as you want. So the elements are going to be very big, but you increase security. But I mean, in front of a quantum adversary, anyway, there's no point in going above. But if we have problem on curves in between, it still works. Okay? So we can prove that this scheme is secure for all the properties under the KMDDH assumption, so under some kind of Diffie-Hellman assumption. And we have a loss in the query made by the linear loss in the query made by the adversaries, but it's not too much. There are tricks if we want to be tight, just we lose a lot on efficiency of the scheme. Okay. So then we need to build our compiler to transform our predicate only is IP to an IP. And in fact, we're more or less going to use it as a plug-and-play version. So we take the setup, we don't change anything. To generate a key, we don't change anything. And it's just when we're going to encrypt, that's the part where it's going to be somewhat inefficient. For each bit of the message, we're going to generate a new value. And so instead of having a vector, we're going to have a matrix of elements to do as a ciphertext. And because it's an IP, we need to think backwards. And so to hide the things, we're going to sort the vector 111 to the values that we compute. That's just, I mean, you can take the convention that you don't need this, but at least here it's more direct when you do the computation. Okay? So we can do this. If we compare to a previous scheme that was building an IP, we are less efficient because now we are relying on the less length of the encrypted message, so it's worse. However, in terms of security, we are much better because instead of being only weak attribute hiding, we are fully attribute hiding. And the previous scheme even had restriction on the kind of queries the adversary was able to do. Here we don't have restriction and we are function private, so we can hide even the secret that is given to the user in the secret key. So that's a trade-off, but it shows that it's doable. There's a compiler that say now if you find a better scheme, then you have a better final scheme, and you don't lose anything in terms of security. Okay. Okay. Then we can consider our second transformation, and it's going to work more or less the same. Here's the identity. We're going to transform it into a vector that's going to be all the exponentiation of the identity up to some value. To encrypt this, we're going to do an interpolation of the identity for some secret coefficient S0 AK, but that's somewhat a classical transformation that you can find anywhere. It's just we're taking the original framework and showing that it can be applied. And to decrypt, that's the part that's a little, in fact, magical. It works exactly the same way as before. You take the master public key, your secret key, the ciphertext, and you run tests on it, and it works. And there's no issue appearing, and you don't need the trick of reversing because the way you embed the polynomial. So the scheme is roughly similar, which is logical because we use the same kind of transformation. You can see the polynomial appearing here, and it's just going to give you a base value to hide in the rest, but it's not too much problematic. The decryption, again, it works the same way. You're going to do pairing computation, check whether those computations are fine or not, and it's going to work. Okay. Sorry. Okay. In terms of efficiency, so we did a previous result where we showed the first transformation of an IBR, but with lots of restriction. So before, when you were revocating a key, you were revocating every possible key for a set of a user. But now you can revoke a key and give a new key for the same user for the same identity that's going to work. Before, we needed to have a binding collusion. It means that beforehand, we had to say that only 10 users can collude, and above that, we don't consider that part of the experiment. Now we don't have this. And we are fully attribute hiding and function preserving. So in terms of master public key, it's not great, because before the master public key was one element. Here we have still something that is linear in both the vector and the encrypted message. However, for the secret key, we have a gain. Before, it was quadratic in the length of the encrypted message. Now it's just linear. And for ciphertext, we are a tiny bit bigger, but of the same order of magnitude. So in this case, the transformation is much better than for the previous one. And we are much better in terms of security, and we don't have an artificial restriction on the kind of attack the adversary can do. Okay? So to conclude, we managed to do several transformations. So the first one is a transformation from a zero inner product encryption to a non-zero inner product encryption. And the key takeaway of doing this is that instead of trying to converge to the same value, we exploit the fact that a zero randomized is still a zero, and while a non-zero randomized is the non-zero. And so we managed to do this in a way that's efficient, and it gives 1 bit of information when you do the decoding. The transformation from this predicate-only IP to an IP, it's the first one that conserves both at the same time the fully attributing property and the function privacy property, because previous papers were focusing on one or the other property. And it's the same for the IP to IBR. And here we managed to be comparable in efficiency or a tiny bit more efficient depending on what property you seek than the current state of the art. The problem is that our transformation is moderately efficient. It's academic efficient, but not practical efficient, let's say, because there's a linear loss in the message length. And the question is, can we do better? So probably, I mean, there's no result that says that we cannot have an efficient transformation. It's just our technique, because we are exploiting one fact on randomizability that gives 1 bit of information, we need to do that for every bit of the message. And so from our approach, this linear loss is there. And we did this transformation from the IP to an IP, and just from a theoretical point of view, it can be interesting to check whether the opposite can be done. And so the efficiency takeaway, it's what I said before. We have some loss for the IP, but we gain in security. For the IBR, we have loss and win, but we are also better in time of security. So thank you for your attention. And if you have questions.
Good morning. My name is Loïc Ferreira from Orange. I am going to present the paper entitled Computational Security Analysis of the full EDHOC Protocol. The context is the following. With the rise of the Internet of Things, an increasing number of end devices are deployed on the field. According to some figures, there may be up to 30 billion active IoT devices by 2030. These devices are leveraged in various use cases. In smart cities, they are used to monitor sensitive sites, to detect fires, or to control air pollution, for instance. Plugged in smart home equipment, they can be used to control heating or lighting. They may also equip medical devices such as pacemakers and defibrillators, which are implanted inside the human body. They are also a component of drones and vehicular systems. And they are also deployed, among other contexts, in industrial IoT to remotely monitor industrial devices. Insofar as all these use cases imply a secure communication link between the remote end device and a server or a ground station, cryptographic mechanisms must be executed by the IoT device, starting with a proper authenticated key exchange to initiate this secure connection. However, these end devices are constrained in terms of resources, in particular regarding the memory footprint, the computation capabilities, and the energy supply. Very often, a critical trade-off, in fact difficult to achieve, has to be found between security and efficiency. And it may happen that the result can be read afterwards in newspapers when they describe successful attacks on some security mechanisms deployed in such low-resource end devices. This illustrates the need for an adequate solution, both in terms of security and efficiency, for this kind of devices. This has motivated the IETF working group, Loïc, to devise a new authenticated key exchange protocol. The result has been named Ephemeral Diffie-Hellman over Cause, or EDHOC for short, and the last EDHOC draft, the number 23, is now RFC 9528. This two-party protocol aims at being lightweight in terms of number of exchange messages during a protocol run, the size of the messages, and the code and memory footprint. Compared to other protocols that one may deem as lightweight enough to be executed by IoT end devices, such as compact TLS or DTLS, EDHOC outperforms these protocols, at least regarding the amount of data exchanged during a run. The EDHOC protocol is essentially based on the Sigma protocol devised by Kravchik in 2003, and it provides 4 different ways for the two communicating parties to authenticate. These parties can use either a signature or a static Diffie-Hellman key. So the initiator and the responder can independently choose the way they will authenticate to each other, which results in 4 different authentication methods and influences on the number of messages. If the initiator authenticates with a signature, then the protocol flow comprises 3 messages, otherwise it comprises 4 messages. The physiognomy of the EDHOC protocol is the following. The key exchange is based on the Diffie-Hellman mechanism. Authentication, as said, is done either with a signature or a static Diffie-Hellman key, and in such a case, a MAC tag is computed with a key derived from the static Diffie-Hellman private key. Identity protection is guaranteed by encrypting the identifiers, which can be public keys or certificates, of the communicating parties, as well as the signatures when they are used. In more details, we can have a look on one of the 4 EDHOC methods, the so-called signature static method. With this method, the initiator authenticates with a static Diffie-Hellman key and the responder with a signature, and the protocol flow is the following. As said, the key exchange phase is essentially done with the Diffie-Hellman mechanism. The responder authenticates first, and it does this with a signature. The signature, together with an identifier, are encrypted to protect the responder's identity. The signature protects a context that gathers a transcript of the messages exchanged so far and the responder's authentication credentials. The signature also covers a MAC tag, which is always computed whatever the authentication method used, that is, with or without a signature. The initiator authenticates with a MAC tag, and this tag is set encrypted together with the initiator's identifier so that the receiver can retrieve the correct credential to verify the MAC tag. This tag is computed with a key derived from the initial Diffie-Hellman key exchange and the initiator's static Diffie-Hellman private key. The data protected by the MAC tag includes a transcript of the messages exchanged so far and the initiator's credential. Then the responder sends an authenticated and encrypted message computed from a key derived from the main shared secret. That is, in this case, the initial Diffie-Hellman key exchange and the initiator's static Diffie-Hellman private key, in addition to other parameters which are related to this specific protocol run. This message proves to the initiator that the responder is indeed able to compute the key material necessary to output the final session key. And the third message, sent by the initiator, fulfills the same function for the responder. Finally, the session key, pure key out, is computed from these shared secrets. EDHOC makes use of the same kind of paradigm as the HKDF scheme devised by Kravchik. That is, an extract function is fed with the different shared secrets, such as the Diffie-Hellman shared secret, in order to provide secret seeds. And an expand function is used to output intermediary symmetric keys and other parameters. The different messages exchanged during each specific protocol run are progressively accumulated and incorporated into the several computations done during the run. The final EDHOC specification is the result of multiple drafts. Several analyses, either with formal methods or in the computational setting, have been made of different such drafts, for instance 12, 14, 17, etc. Regarding the computational analysis, only one different authentication method has been scrutinized. Moreover, the security models used in these works do not incorporate exactly the same security properties. So what we have done is first to devise a strong security model that captures all these different security properties. Our computational security analysis also covers the different changes that have been made successively after the different previous security analyses. And we have considered the 4 EDHOC authentication methods instead of one only. Finally, from our theoretical security bounds, we have computed concrete estimates for these bounds, based on different possible adversarial resources. EDHOC proposes different cipher suites, and these concrete estimates enable to choose the proper cipher suite depending on the actual context the protocol is deployed. The security properties captured by our model are the following. First, entity authentication. Informally, this guarantees that an instance ending in accepting state has one and only one communicating partner during the protocol run. Key indistinguishability guarantees that the final session key is indistinguishable from a value from the same set of keys uniformly chosen at random. Forward secrecy bears on the security of the past sessions when a long-term secret is disclosed. Finally, identity privacy guarantees that the identity of the parties involved in a protocol run remains confidential, and also that different protocol runs cannot be linked, which forbids an adversary from tracking a given party. This security property is based on the notion of virtual identifier, and during the corresponding security experiment, the adversary chooses 2 identities, and the challenger runs the protocol with 1 out of 2. The attacker's goal is then to guess which party is actually involved in the protocol execution. The adversary can basically do anything but to get access to the session state, as long as this does not lead to trivial attacks. That is, an attack which essentially is unavoidable and does not depend on the protocol features. More precisely, the adversary is active. It controls all communication and can forward, alter, drop any message exchanged by honest party, or insert new messages. It can corrupt long-term keys, reveal session keys, and unmask identities. So we provide theoretical bounds, security bounds for all EDHOC authentication methods. We establish the protocol security based on the Strong and Gap Diffie-Hellman assumptions, mainly, for the key indistinguishability property, the unforgeability of the signature scheme or the MAC function, depending on the EDHOC method, for the entity authentication property, and the ciphertext indistinguishability provided by the symmetric key functions for the identity privacy property. As said earlier, different cipher suites are available in EDHOC. The specification defines in particular 2 cipher suites for high security applications. One is based on AES 256 and the other on SHA-20. From the theoretical security bound that we get, we can compute concrete estimates based on different adversarial resources in terms of computation and time. And these estimates show that the cipher suite based on AES 256 appears more suitable for such high security applications. To sum up, we have performed a computational security analysis of the EDHOC protocol and its 4 authentication methods. In a strong security model, we have got theoretical security bounds, which in turn enable to compute concrete estimates based on various adversarial resources. And these estimates can be used to choose the proper EDHOC cipher suite depending on the context of use. We have also shown in particular that the cipher suite based on AES 256 appears preferable for high security applications. Finally, in the context of the threat posed by the development of quantum computing and the post-quantum transition, a challenging area of future research is to devise a quantum-resistant version of the EDHOC protocol. This ends my presentation, and I thank you for your attention.